Hi 242. In this video I would just like to finish up 10.4 by talking about one last little concept that we weren't able to squeeze in when we finished 10.4, and also I wanted to work through another example of using the four-step process with you because I felt like we could use one more of those. So the one thing I wanted to talk about to finish this in this section was that we need to talk a little bit more about this derivative, the definition of this derivative. Now I've written the definition of the derivative of f at a, right? So remember, this is the derivative of f at x equals a, right? This is the derivative at a specific place, right? Remember, this will actually equal a number because we would have a value for a here, right? We would have like 3 or 2 or 0 or something like that, right? So this actually equals a number. Okay, and remember, this number is what? The slope of the tangent line to f at a, right? And so this equals slope of tangent line to f at x equals a. Okay, that's what the derivative means by definition. Okay, well, remember that this is the result of a limit, right? It's the limit of this expression. And we're saying that it equals a number, but if we remember back to our work with limits, a limit doesn't always have to exist, right? A limit may not actually exist. It might not actually equal a number. Okay, and when that actually does happen, when you're doing the limit process here to calculate the derivative, and you get something that isn't a number, right? When you say it does not exist, if you say the result of this limit does not exist, well then we have to use some special words for that since we're talking about the derivative. So we should make sort of a little note to ourselves here that says if this limit does not exist, right? Remember, we say DNE for does not exist. Then we can say something like, we say f is non-differentiable at a. Okay? So if this limit does not have an actual specific number that it equals, then we say that the function f is non-differentiable at a. Okay. Otherwise, if it does equal a number, we say it is differentiable. Okay, so we can say if limit does exist, okay, then f is differentiable. Okay, and that word differentiable is equivalent to saying that we can find the derivative at a. Okay. Okay, good. So we can use the words non-differentiable if this limit doesn't exist, right? If we try calculating this limit and we get like a big old infinity or something like that, we say it's non-differentiable at a. And if the limit does exist and we actually get a number here for the slope of the tangent line, then we say that it is differentiable there. Okay, and there's an easy way to tell just by looking at the graph to determine if a function is differentiable or non-differentiable at a location. So let's see how this works graphically to determine whether it's differentiable or not, right? If I had something like this, okay, and let's say this is the function f here. Remember that the derivative of this at a location is the slope of the tangent line. So let me get a different color here. So if we were moving along, if we were sort of asking ourselves, where do we want to look at the slope of a tangent line, we could just pick a spot, I don't know, right there maybe, right? And if we can draw a tangent line, well, what that means is that there is a slope for that tangent line, so that the derivative exists at that place, right? Okay, so since I can draw a tangent line there, that means that the derivative exists at that place. The function is differentiable at that place, right? So if we called this a or something here, right? Because we can draw a tangent line there, that tangent line will have a slope, then what we do is we say, well, that means that f is differentiable at a. Okay, and we can do this in lots of places, right? We could do this over here, maybe with a different color. We could do this here, like this, another tangent line, okay? And again, maybe at b here, we have a tangent line. It has a slope, so what that means is it's differentiable at b, and there's actually a number that we could associate with the derivative at b. But let's think about if we are Let's try purple. What about like right here? Okay, if we were to draw a dot there, let's say let's consider this C, okay? If that's C here, how do we draw a tangent line? Well, this is sort of an issue because look, there's like lots of options. It's kind of like the top of it, like a seesaw, you know what I mean? You could put it like that, but you could also put it like this, right? You could put it like this. We kind of don't know how to set it on there, right? So since we actually can't figure out how the tangent line should look, we don't know what its slope would be then, right? And that's the difference in all of these lines is their slopes are all different. We don't know how to set it on there. So what that means is that at that place right there, we say f is not differentiable at C. So f not differentiable at C, at x equals C. Okay, and that's true in general. If you have something funny going on, like a corner like this, or a cusp or something, then you're not going to be differentiable at that place. So corners and cusps are definitely bad. Vertical asymptotes are bad. Holes are bad. To see a reference of the C figure, let's see, no, figure 8 on page 523 of your textbook. Okay, and that gives you 4 examples of features of a graph where a derivative will not exist, right? Where it's non-differentiable. Okay, so breaks are bad, sharp corners, vertical tangent lines are obviously bad because their slope is not defined, and cusps, something like this, right? Where you have this sort of pointy thing like that. Okay, those are all examples of places where we have non-differentiable. Okay, so let's finish this short video up with doing one example of using the 4-step process to find an actual derivative itself. Okay, so let's, because I know we did one quickly together, but let's do another one together. So let's try doing something like, let's see, how about if we take the function x squared minus 1, okay, and we wanted to try to figure out f prime of x. Or actually, let's be more specific. Let's find f prime at 3. Okay. Well, we have some options. If we want to find f prime at 3, what we can do is we can write, well, I know what f prime at a is by definition, right? It's the limit as h approaches 0, f of a plus h minus f of a all over h. And then what I could do is say, well, in this case, I'm looking for when a is 3, right? So what that means is I could replace all of these a's with a 3. Right, so 3 here, and 3 here. Okay, so that means I could actually rewrite this so that f prime of 3 is the limit as h approaches 0, and I just have to do what? Plug in 3 plus h into the function. So that means I do 3 plus h squared minus 1, because that's, remember I put 3 plus h here, square it and subtract 1, minus the function at 3. Well, what is f of 3? F of 3 is what? 3 squared is 9 minus 1 is 8 all over h. Okay. Now we can work this actually out by squaring things out and canceling terms. So this is what? 9 plus 6h plus h squared minus 9 all over h. And the 9's cancel. So 9's cancel away. I'll use another color for that. Okay, and then remember that the h's can actually cancel as well. I can cancel 1 in each term with the 1 in the bottom. And so all I'm left with then is 6 plus h. And when h goes to 0, that means this is just 6. Okay, and this number, remember, tells you what? The slope of the tangent line to f when x is 3, right? The slope of that line at 3 would be 6, right? So if you're thinking about this graphically here, x squared minus 1 looks something like this. It's a parabola shifted down 1 unit. And at 3, when x is 3, that would be what? So let's see, 1, 2, 3. Okay, at 3, we were looking here. And I will use another color for that. At 3, we're here. If you are to draw the tangent line there, the slope of that line would be 6. Okay, the slope of that line, the slope m, is 6. But remember, we don't use m anymore because we have derivatives, right? So we say f prime at 3 is 6. Okay, there's an alternative way you could have done this, of course, because we know how to find f prime of x as an actual like function itself, right? We could have found it as a rule here using this definition for the limit, right? Where we just change all of those a's to x's to keep everything really general and really sort of more useful for us to just plug in values of x later. Okay, we could have gone through this entire process here and come up with a rule, and let's just see how that works. So I again do what? I put in x plus h. Well, that says that we do x plus h squared minus 1 minus, what is f of x? X squared minus 1, but I have to be careful to subtract away all of f of x divided by h. And now we can expand things out. X squared plus 2xh plus h squared minus 1. That's that minus 1 right there. And then minus x squared plus 1 for everything that's happening right here in this second part, all over h. Oops, and I forgot my limit out front. That's really bad. Remember, this doesn't turn into a tangent line if you don't have that limit out front, so that's really important. Okay, things cancel, of course. So we have the x squareds are gone, 1's are gone, and then remember we're able to cancel some of those h's, and h in each term with the 1 in the bottom. And we're left with 2x plus h. And when h goes to 0, we get 2x. Okay, so that means here that I know f prime of x as a function is 2x. And if I wanted f prime at 3, I would do what? Plug in 3, so 2 times 3, which is 6. And hello, we got the same answer. The reason for that is because the derivative, the slope of the tangent line at 3, should be 6, right? So of course these two methods should return the same answer. Okay, so that's the last bit I wanted to do for 10.4. Hopefully you enjoyed the video.